Yes, start. Welcome to one and all. Today we are going to discuss about measure and integration. And in this measure and integration, we are going to see what is measure on real line, integration of function of real line, abstracts measure space, convergence, signed measure and their derivatives, and finally measure and integration in a product space. All the sets considered in this topic are contained in R and the real line unless stated otherwise. We will be concerned particularly with interval I of the form I equal to half open interval of a comma b, where a and b are finite unless specified otherwise. By an interval, we shall only mean a interval of the above types. If a equal to b, then I is an empty set pi. We will denote the length of the interval, that is b minus a by L of I. And now we are going to see Lebesgue outer measure. The Lebesgue outer measure are, more briefly, the outer measure of a set is given by m star of a equal to infimum of summation L of in, where the infimum is taken over all finite or countable collection of interval in, such that a is a subset of union of in. And next, measurable set. The set E is Lebesgue measurable, or more briefly measurable if for each set A we have m star of A equal to m star of A intersection E plus m star of A intersection complement of E. The next, sigma algebra. A class of subset of an arbitrary space X is said to be a sigma algebra or a sigma field if X belongs to the class and the class is closed under the formation of countable unions and of complements. Next, Borel set. The sigma algebra generated by the class of intervals of the form A equal to half open interval of a comma b. Its members are called as Borel set of R and it's denoted by cursive b. The next, integration of non-negative function. Now we consider first the class of non-negative measurable function. Define the interval of such a function and examine the properties of the integral. For the present, we will suppose this function to be defined for all real x. And a non-negative finite valued function pi of x taking only a finite number of different values is called a simple function. If a1, a2 up to an are the distinct value taken by pi and ai equal to x, where pi of x equal to ai, then clearly pi of x equal to summation I equal to 1 to n ai x ai of x. The set ai are measurable if pi is a measurable function. And now let pi be a measurable simple function. Then integral over pi dx equal to summation I equal to 1 to n ai m of ai is called the integral of pi. Next we see a integrable function. If f is a integrable function and integral over f plus dx is less than infinity and integral over f minus dx is less than infinity, then we say that f is integrable and its integral is given by integral over f dx equal to integral over f plus dx minus integral over f minus dx. Next we are going to discuss about definition of measurable as applied to sets and functions or provided for abstract measure space. We show that a measure on a ring of sets can be extended to one on a generated sigma ring. What is a ring? A class of sets R of some fixed space is called a ring. If whenever E belongs to R and F belongs to R, then E union F and E minus F belongs to R. A ring is called a sigma ring if it's closed under the formation of countable union. A measure mu on R is complete if whenever E belongs to R, F is a subset of E and mu of E equal to 0. Then F belongs to R. Now coming to the measure space. We started with the ring of finite unions of interval of the form half open interval of a comma b and obtained the sigma ring of measurable set. In that case, the sigma ring obtained was a sigma algebra since a sigma algebra is a most frequently occurring case, we require ourselves of this is follows. A pair of x comma s where S is a sigma algebra of subset of a space X. That is, the subset is called a measurable space and then the set of S are called a measurable sets. Okay, thank you.